Hello everybody. So we are moving on to lecture number 8 now. So over the next couple of lectures we're going to be thinking about sedimentary rocks and what they actually tell us about the history of the surface of the Earth. Okay, so obviously no one was around millions of years ago to observe the deposition of sediments that went to form sedimentary rocks. So this means that we must apply the principle of uniformitarianism to explain the compositions and textures observed in sedimentary rocks. However, in order to make such comparisons, we must have a solid bank of evidence and observations that support our inferences. So when we look at a sedimentary rock, essentially, we need to have evidence from modern systems to back up the assumptions we're making. So igneous and metamorphic rocks provide substantial evidence on the composition of the Earth, the movement in terms of plate tectonics, volcanism, changes in pressure, temperature, etc., etc., etc. So there's lots of information you can get from igneous and metamorphic rocks. However, sedimentary rocks are often of much greater use to geologists because, number one, they preserve evidence of the surface processes responsible for deposition, running water, wind, waves, glaciers, etc. And number two, they contain fossils. And fossils can tell us about the environment, and they also allow us to relatively date rocks. So even though there's lots of information in igneous and metamorphic rocks, when it really comes down to it, if you are dealing with any portion of geology that is focused on the surface of the Earth, most of the time the best rocks to use will be sedimentary rocks. So geologists look at areas where sediment is being deposited now, and we term these depositional environments. And for each depositional environment, we'll produce a set of criteria that define them. So we'll look at the types of class that are present in the sediments. Are they big class, small class? Are the class well-rounded, poorly rounded? Are they well-sorted, poorly sorted? And then we'll look at the structures that form. Are there crossbeds, ripple marks, mud cracks? And then we'll also look at other things like the types of fossils that occur there. And by looking at all this information and putting it all together, we essentially end up with a set of criteria. So for each depositional environment, there's a set of things we look for that allows us to essentially say, right, this sediment was deposited by, let's say, a river. Now, once we have those set of criteria that allows us to identify sediments deposited by a river, then we can take those criteria and we can apply them to rocks. So we can look at a rock and we can say, right, well, I can see exactly the same things in this rock that I see in these sediments that I know were deposited by rivers. As such, I can therefore relatively strongly assume that this rock was deposited by, this sediment that went to form this rock was deposited by a river. And that's the basic idea. Principle of uniformitarianism. If it's happening now, it's happened in the past. And it's a relatively solid idea. So when we visit an outcrop of rocks, geologists will note several features. We'll also look at the rock's colour, the rock's composition, the rock's textures, and the rock's fossils. So things, the colour, the composition, the textures, and the fossils, that's going to help us in a lot of cases to work out exactly what type of environment the sediment was deposited in. Then we're going to look at the thickness, and that's going to tell us about how quickly sediment was being deposited. And then we're going to look at the relationship to other rocks. So essentially how the rocks, the position of the rocks in the sequence of rocks, or the shape that that particular body of rock has, can tell us a lot about the type of environment in which that sediment was deposited. So each of these 6 factors combined will allow us to build up a bank of evidence from which we will say, right, it was probably deposited in this depositional environment. So there are a few things we need to think about. So let's think about colour first of all. Now, in the vast majority of cases, most sedimentary rocks vary somewhere between a light grey and a dark grey. So in most cases, they're not particularly helpful to us. So colour is not that great. However, in some cases, the colour of the rock can give us some indications. So if your sedimentary rock has a red colour, it's likely to have been formed on land, often in arid conditions. So in about 90% of cases, if you come across a sedimentary rock that has a red colour, you can say, right, chances are this rock was deposited in, desert or semi-desert conditions. In contrast, if you come across a rock that has a greenish colour, well, that rock is likely to have been deposited in a marine environment. Okay? So if you come across, let's say a mudstone that has a slight green tint to it, you can think, there's a good chance that this mudstone was probably deposited in a marine environment. All right. Now, in terms of the red colour, that actually works about 90% of the time. In terms of the green colour, that's probably effective about 70-75% of the time. Obviously, for both cases, there are exceptions to the rule. So geologists will take a sample of any rock that they find at an outcrop, and we'll look at these rocks these samples we take in hand specimen. We will look at them down a microscope, and in some cases we'll actually subject them to chemical analysis. So in the case of looking at them down a microscope, why do we do that? Well, number one, it allows us to very accurately look at the composition of the rock. So, when you're dealing with something like a sandstone, it can often be quite difficult to distinguish between, let's say, what's quartz and what's plagioclase feldspar. It can be quite a tough thing to distinguish. Look at it down a microscope, the difference is plain to see, and you can very quickly work out what the exact composition is. Also, when you look down a microscope, it allows you to look at the fossils, and that's very, very important. There is a lot of information in microfossils, organisms that we can't really see. So, so every morning, you get up, you have a glass of water. In that glass of water, although you can't see them, there are going to be absolutely tons of little organisms, and they don't do you any harm. Well, as long as the water's clean. So, and those organisms, essentially, if they have some kind of shell, and the shell can be fossilized, well, that shell can tell us what organism was living in the water, and therefore, if we know what organism was living in the water, that allows us to infer the conditions at which the water existed. So, it gives us ideas of things like temperature, or salinity, or the amount of oxygen in the water. And once again, that's very, very important. So, if we find, rocks that give us strong indications from the fossils that there was very little oxygen in the water, well, that only occurs in a relatively limited set of environments. And so once we know that, we can begin to make, inferences. Or other things like, if we look at the fossils and we see that it's, contains an organism called a diatom. Well, diatoms only like to live in relatively cold water towards the poles. So once again, the second we start seeing diatom fossils, that instantly makes us think, well, this was in some kind of cold water environment, and it would have been located somewhere towards the poles. So instantly that means we can discount, this sediment was deposited in a tropical regime. That can go straight out the window. In some cases, we will also subject samples to chemical analysis. And chemical analysis is done in one of two ways. There's something we refer to as a point analysis, and that's when you analyze a very, very small area of your sample, typically a single crystal. And you can do that using tools like a scanning electron microscope, which is something you might have heard of. The other way you can analyze a rock is what's called a bulk analysis. And in a bulk analysis, you typically take the whole rock and you'll typically dissolve it in acid, so you end up with a liquid. Then you'll run that liquid through a piece of equipment called a mass spectrometer, and that will tell you the elements that are present in that rock. And that's a technique that's commonly used in oil exploration when you want to know exactly how much carbon there is in a rock. If you're thinking, was this rock a source rock for oil or wasn't it? Okay, so when we take our piece of rock from the outcrop, we'll turn it into a thin section. So a thin section is when we take a slice of rock that's so thin that light will actually transmit through the mineral. So the light will come from the bottom of the slide and come out the other side so we can see the minerals. And so this is what we typically see when we look down a microscope. And you can see in this particular case, well, at least I know, there's two very obvious minerals. The first mineral is quartz. And all these crystals that have this kind of grey colour, that's quartz. In between them, we have this mineral that has a kind of yellow colour. That's the mineral calcite. So I know instantly what I'm looking at here is a sandstone that's clearly got a calcite cement. Now, once again, that's instantly going to tell me quite a lot. I can look at number one, the shape of the crystals. Are the crystals well rounded? Well, on the whole, they're kind of sub-rounded, so they haven't been transported for that long. At the same time, we can see they have a calcite cement. Well, there's only a few environments where I can have a sand that gets cemented together by calcite. So typically, when I see something like this, I'm going to think this is probably a marine sandstone. It's forming at or just off the coast, in all likelihood. Probably in a warmish environment. Another thing we can look for are the microfossils. So this is a microfossil of an organism called a foraminifera. And foraminifera, there are lots of different species of them, and each different species will typically have the temperature regime that it likes to live in. So it'll only live in a certain water temperature. That water has to have a certain salinity, a certain amount of oxygen. and so that can tell us quite a lot about the water conditions in which the sediment was being deposited. Now, in some cases we can go to even finer detail, and this is when we use things like a scanning electron microscope, and this allows us to look at structures that are even beyond the range of a microscopic analysis. And this allows us to see things like individual plates of clay minerals, and that in some cases can be quite helpful to us. Most of the time not, but sometimes it can be. So, where possible, the field data will be used to produce a geologic cross-section displaying the vertical and lateral relationship. So we want to see, we have the sequence of rocks going up from oldest to youngest, but we'll also have a diagram that shows us what's happening to the rocks laterally. Are they just nice horizontal layers? Are they folded? Are they faulted? All these things need to be thought about. So, using all this data, a comparison is made to modern-day depositional environments, and everything is combined, and it's used to produce an environmental interpretation. And essentially from that, we try and work out what environment was this sediment deposited. What was the depositional environment? So, analysing the rocks in this way not only makes for great science, but it also is also of more use economically. So, by mapping and producing cross sections, you can identify possible oil and gas reservoirs. By looking at sandstones down microscopes, you can see whether it's porosity and permeability makes it a suitable reservoir rock for oil or gas. And microscopic and bulk analysis of mudstones can tell us about how much carbon was present in the rock and whether that rock has been heated up. And if a very carbon-rich mudstone gets heated up, it'll start to produce oil and gas, which will obviously end up in a reservoir rock like a sandstone. Very recently, I'm sure you guys have started hearing more and more about electric cars. And in electric cars, you require lots and lots of batteries. And most of the batteries that are used now are lithium-ion batteries. So at the moment, there's a growing market for lithium. They need it to make batteries. And when it comes to lithium mining, it's done using sedimentary rocks. And so once again, having a good knowledge of sedimentary rocks allows you to very quickly work out the types of rocks and the types of historic environments that lithium deposits could have formed in. And so, as a mining geologist like I am, I would look for those criteria, look at the criteria I was looking for, try and find places on the surface of the earth that met those criteria, and then I would go on the hunt and see if I could find some lithium to mine. Okay, so let's think about the composition and texture of sedimentary rocks. So we need to remember that sedimentary rocks are split into three broad groups. There are the detrital or clastic sedimentary rocks. So those are sedimentary rocks that are made up of solid particles of pre-existing rock or minerals. There are the carbonates. Those are sedimentary rocks formed from the concentration of shells and corals or through the precipitation of carbonate from solution by organic activity. Okay? So essentially anywhere we have large quantities of carbonate material building up, that carbonate material can then be compressed and liquefied to give us a limestone. And then we have chemical sedimentary rocks, and those are produced by the deposition of dissolved phases, typically carbonates, caused by changes in temperature, pressure, fluid chemistry, or the activity of organisms. So that's when there's some change, and that change causes a fluid that contains dissolved minerals, typically calcium carbonate, to deposit those minerals. So, sorry about this slide, I can see there's a lot of words on it, but we're going to work our way through them. So, detrital rocks can consist of more than 100 possible minerals. But when it really comes down to it, quartz, feldspar, and clay minerals are by far and away the most common. And there's two reasons for that. Number one, quartz and feldspar are very physically robust minerals. They don't break down very, very easily. So they can be transported by rivers over very, very large distances, and the crystals will survive. Compare that to something like biotite. Biotite is a naturally soft mineral, and so if you have a crystal of biotite being transported by a river, it will bang into other stuff, and it will very quickly fall to pieces and be lost. So quartz and feldspar persist because they're such physically robust minerals. The other reason that a mineral can persist for a long period of time is if it's chemically inactive. So feldspar will slowly, very, very slowly, but it will slowly react with water, and it will turn into clays. So the longer feldspar is exposed to water, the less and less feldspar you'll have, because it will chemically start to break down. Very slowly though. So if feldspar is transported for a very, very long period of time by water, the feldspar will slowly but surely begin to degrade and be lost. Now compare that to something like quartz and clays. Quartz and clays, on the other hand, are very, very chemically inactive. So they're not going to react with stuff like water. So in a sedimentary environment like a river, they'll just happily be transported along and they won't change in any way. So these three minerals persist because, number one, they are physically robust, or two, they are chemically robust, or in the case of quartz, both. So the composition of a detrital rock is primarily controlled by the composition of the rocks in the area from which the sediment was derived. So that's termed the source area. So if you are weathering a granite, well, the sediment you're going to initially produce will obviously be rich in quartz, feldspar, probably some biotite, okay, maybe some muscovite. And so obviously that means the sediment that's being produced is a direct reflection of the rock being broken down. However, it's not the only factor, and doesn't actually tell us that much because these minerals can be sourced from a host of completely different terrains. So once again, if I come across a sediment that consists of lots of quartz and feldspar, I can think, right, well, that rock could have come from the weathering of a granite. On the other hand, it could have come from the weathering of a sandstone. On the other hand, it could have come from the weathering of a quartzite. So, but the mineral composition of a sediment doesn't actually tell me too much about the source area. It gives me some ideas about it, but in the vast majority of cases, it doesn't tell me that much. Now, there are some times when the sediment can tell me quite a lot. So, for instance, if you were to go to Hawaii, Hawaii is well known for having black beaches, and that's because the minerals that make up the sand in those beaches are derived from the basalts that make up most of the island. And so when you have black sands like that, you can say, right, well, in that case, I can actually make some relatively solid, assumptions about where this sediment came from. But in the vast majority of cases, most sediments can't be tied down to one particular type of rock from which they came. So the composition of a sediment is, of course, as we mentioned, also affected by the degree of maturity. So maturity essentially comes in two forms: physical maturity and chemical maturity. So chemical maturity we've already discussed. So as a sediment gets transported, chemically reactive minerals will break down. And so over time, the sediment will become richer and richer in chemically inactive minerals like quartz and clays. So that's chemical maturity. Then there's physical maturity. That means over time, soft minerals will get broken down and hard minerals will continue to persist as a sediment gets transported further and further. So essentially, as a sediment gets transported, let's say by a river over very long periods of time, the amount of quartz, feldspar and clays will increase as softer minerals like biotite, muscovite will slowly be broken down and lost. So when we look at sediments and we say, right, well, this sediment contains crystals of minerals like biotite and muscovite. So that gives us an instant indicator that chances are this sediment wasn't transported for too long, otherwise they would have been lost. The other thing we can look for is we can look at the clasts themselves, and we can look at the clast roundness and the clast size, and that also gives us some idea about how long the sediment was transported for. So if a sediment contains a lot of clasts that are very the same size, that's a very well sorted sedimentary rock, and those clasts within that well sorted sedimentary rock are nice and round, we can say, right, this sediment has been transported for a long period of time. It is therefore a mature rock. In contrast, if I look at a sedimentary rock that contains a very wide range of clast sizes, so I have everything from clays to boulders, and all those clasts are quite angular in shape, well, that instantly tells me that that rock is a relatively immature sedimentary rock, so the sediment wasn't transported that far. So, so by looking at the composition and some of the textures of the rock, that instantly allows me to start making assumptions about what's happened in its history. So the grain size of the detrital rocks tells us about the conditions of transport and deposition. So here's some examples. So gravel-sized rocks can only be transported by energetic processes, like fast-flowing water, landslides, strong waves, or glaciers. So if I see a sedimentary rock that consists of very, very coarse clasts, gravels, cobbles, and boulders, I know that rock can only have come from a high-energy environment. So I instantly know that rock will not have formed in a lagoon, for instance. I know it has to have come from some environment that had a lot of energy to move those clasts. Sand-sized clasts, on the other hand, only require a moderate to energetic environment to move them around. So they can be moved by things like rivers, the wind, or waves, or moderate strong waves on beaches. And then we have clay and silt-sized clasts. Well, they require only a relatively low energy to move them. So they can be essentially moved by systems that have only a very, very low velocity and therefore a relatively low energy. That includes environments like, very slow-flowing mature rivers or lakes or lagoons, or the abyssal plain environment we find in the deep oceans. So first of all, instantly by looking at the class size, I can start making sweeping assumptions about the kind of general environment in which my sediment was probably deposited. So these two diagrams here are just to discuss the transportation energy and the depositional energy. So in terms of transporting a sediment, in a high energy environment like a really fast flowing mountain river, well obviously you can transport a large range of class sizes, everything from gravels all the way down to silts and muds. So we would expect that to be reflected in the sediment. Moderate energy environments like rivers would typically only be able to transport sands and silts and muds. Obviously they would not have enough energy to transport gravels. And in very low energy environments like a lake, for instance, or a lagoon, well the water in those environments would only have the energy to transport very, very fine particles like silt and mud. That water would be incapable of transporting sediment sizes like sands, gravels, cobbles and boulders, for instance. So the energy of the transporting medium is reflected in the class it can transport, and therefore the class we see when they are deposited. So a high energy system like a very fast flowing river, well that will only deposit quite coarse class sizes. So think of a fast moving mountain river, it's got lots of energy, it's going to move those big clasts around, then eventually it's going to start running out of energy and it's going to have to deposit those large clasts. And so when we see a sedimentary rock that's made up of these nice big clasts, we're going to instantly go, right, this was some kind of very energetic, high energy environment. Now the thing is because the water is still quite energetic, the sand, the silt and the mud, well they'll still be transported away. So rocks that form in very high energy environments tend to contain lots of large clasts, but the small clasts tend to have been transported further downstream, so they don't actually end up in the rock. So then we have moderate energy environments. So in the case of moderate energy environments were never capable of transporting gravels. So we instantly know, well, moderate energy environments should not have anything coarser than the sand. Now, that means that as soon as a moderate energy transporting medium starts to lose energy, like the wind or a river, as soon as it starts to lose energy, it's going to start depositing the sand-sized clasts. In the case of the muds and the silts, on the other hand, well, they're so fine-grained that once again, they're not going to be deposited. The river will still have enough velocity to transport those sediments, so they're going to be transported away. So we know that sand-sized clasts will tend to be associated with moderate energy environments. In the case of low energy environments, well, low energy, very slow-flowing water, for instance, will not have the capacity to transport gravels or sand. So that means that the only type of sedimentary rock that can form in a low energy environment will be a sedimentary rock that's produced from the smallest grain sizes, in this case silts and clays. So by looking at the class within a sedimentary rock, we can make assumptions about the type of energy, about the energy of the environment that deposited or into that the sediment was deposited into. Alright, so it's been 20 minutes, well over 20 minutes actually, so this is a good place to stop, take a break, pause the presentation, go and get a glass of water, have a walk around, and then come back in a couple of minutes. Okay, everyone. So before we start the second part, the next part, should I say, let's take a second just to do the code word. So the code word for this presentation is going to be thunder. That's as in thunder and lightning. So that's the code word is thunder. Okay, so on to the next slide. So next we have to think about texture. So texture refers to observations about the class present in a rock, so a sedimentary rock should I say. So we're going to look at the size distribution, the shape and the arrangement. So the class shape is a reflection of the degree of rounding. How round are the class? Are they spherical or are they very, very angular? So the longer a detrital grain is transported for, the more opportunity it has to hit other clasts in the bed load, and every time it hits another clast, it will knock off a corner. So over time the clasts become more rounded and they'll begin to move towards a more spherical or elliptical form. So the longer a sediment is transported for, the more rounded the clasts will become. So the energy of the environment also plays a part in the rounding. The higher the energy of the environment, the more rapidly the clasts will collide into each other, therefore the faster the clasts will begin to round. So if we look at sediments that are deposited by fast-flowing mountain streams, because they're very, very fast-flowing, you have a very, very wide range of clast sizes, everything from really big boulders all the way down to smaller sand-sized clasts. But when we look at those clasts, we'll actually see they are surprisingly well-rounded. That's because although they're being, it's a high-energy environment, so you'd expect quite a poorly sorted sediment, the clasts themselves are quite well-rounded because they're banging into each other very, very often, and that means they round off pretty quickly. Now, when we're talking about rounding, we only talk about anything that's sand, gravel, cobble, or boulder sized. We don't worry about silts and clays because they are not transported as part of the bed load. They're actually held in suspension in the water of, let's say, the river or in the air. They're too small, essentially too fine to actually bang into each other. So they never round. So when we're talking about clast rounding, we don't care about silt and clay sized particles. So we have rounding, that's the first thing. The longer a sediment is transported for, the more round it will become. The more energetic a sediment, the more energetic the environment the sediment's being transported in, the faster it will round. So we can then look at the class size distribution, and that's essentially a reflection of the degree of sorting. So a well-sorted sedimentary rock will have a very tight range of class sizes. So if I go to a desert like the Sahara and I look at the sand that makes up that desert, I can say with relative certainty that the size of the class in that sand is going to be very, very restricted. There's going to be a very small range of sizes. So that's going to be a very well-sorted sediment. In contrast, a landslide is just when a whole load of rock falls off the side of a cliff. So everything just comes flying down the side of the cliff, and then eventually when it reaches the bottom of the cliff, it just stops moving because it loses velocity. So in that case, all you've done is you've had a point of sediment move from point A at the top of the cliff to point B at the bottom of the cliff, and there's been no time for any sorting to take place. So rocks related to landslides are very poorly sorted. We'll have everything from clay-sized particles all the way up to boulders. So well-sorted rocks have a very tight range of class sizes. Poorly sorted rock has a very broad range of class sizes. So once again, as with rounding, the degree of sorting is a reflection of the sediment's maturity. The more mature the sediment is, the better sorted it is. So the longer it's been transported for, the better sorted it will be. So as a sediment is transported, larger clasts knock into each other and they break into smaller clasts. So over time the sediment will develop a tight range of class sizes as bigger clasts are lost and replaced by smaller clasts. So once again, the strength of the transporting medium also plays a part. So in high energy systems, like a glacier, glaciers are extremely high energy. They can transport everything from clays all the way up to massive boulders the size of 4-bedroom houses. So they have the strength to transport a broad range of class sizes. So that typically means the sediment that's produced by a glacier will have a very, very poorly sorted class size distribution. They'll have everything from small class all the way up to very, very large class. In contrast, the wind, on the other hand, can only transport sediments of a very limited size because it only has a limited energy. So the wind can't transport boulders, gravels, and cobbles. So it can't move those at all. All it can transport is sand, silt and clay. Now the wind will take the sand, silt and clay and it will transport it away out of the area, leaving behind just the sand. And that's why deserts are mostly covered in sand, because the wind can't move the larger clasts, and the smaller clasts, the silts and clays, get transported out of the area. And so all that gets left behind is a big pile of sand. And so once again, that tells us something about the system we're in. So if we have a sediment that consists just of sand, that's going to give us some indications of the likely environment it could have formed in and the energy of that environment. So it should be noted that if transported for an extended period of time, glacial sediments will become better sorted. So okay, so these diagrams here are just going to give you some kind of idea. So here we have, these are the different different classifications of sorting, from very poorly sorted down here, a very broad range of class sizes, everything from very, very small class to very, very large class, to a very well sorted rock up here where you can see the class are mostly the same size. And we can look at this rock over here. So this is the picture we saw earlier, this sandstone. And we can see here are quartz crystals, and you can see the quartz class are on the whole of a very similar size. So, that's going to make us think, well, this sandstone is, between well sorted and very well sorted in terms of its maturity. And so that would suggest it was a relatively mature sandstone. In contrast, if we look at this conglomerate down here, we can see it consists of lots of cobble and gravel sized class, the larger ones that are quite easy to see, and in between them we have lots of much smaller material. It looks quite sandy, and so, well, that's obviously a poorly sorted sediment, so that would suggest it's a relatively immature sediment. Now, the one thing you will notice there is when you look at the class here, they're not super well rounded, but they don't have a lot of sharp corners, and so that's going to tell us something as well. The fact that they are, partially rounded suggests that even though the sediment hasn't been transported for that long, because it's very poorly sorted, it suggests that whatever was doing the transporting must have been quite energetic in order to round those clasts quickly. And so something like a nice fast-flowing mountain river would probably be a really good environment for the deposition of this type of sediment. So the next thing is sedimentary structures, and sedimentary structures are extremely important when we try and think about the likely depositional environment of a sedimentary rock. So most sedimentary rocks contain structures that form during deposition or shortly afterwards, but the most important thing is these structures formed before the sediment was lithified into a rock. So these structures reflect both physical and biological processes, and as such they are the most useful tool in analysing how deposition took place. So we geologists know how these structures form, as sedimentary geologists have worked hard to find modern examples. So for each structure you can see in a sedimentary rock, geologists have gone out and they've tried to look at the modern environments in which these structures occur. So these modern examples provide the predicted conditions under which the geologic structures will have formed. Okay, so to begin with, we're going to start looking at the common physical sedimentary structures. So the most common structure is stratification or bedding. So as we know, rocks tend to come in layers, especially sedimentary rocks. And so each sedimentary rock, each layer of sedimentary rock, depending on its size, can be classified in one of two ways. If the layer has a thickness of less than 1 centimeter, that layer is referred to as a lamination. If the layer has a thickness of greater than 1 centimeter, it's referred to as a bed. So laminations are most common in mud rocks. Mud rocks form in relatively low energy environments. So when we see a rock that consists of laminations, we can say, right, this was probably a relatively low energy environment where the water wasn't moving very fast, if at all, and that means that the silt and clay that's held in suspension in the water will slowly begin to fall out of the water and settle onto, let's say, the floor of the lake. And that's a very slow, gradual process that produces lots and lots of very, very fine, thin layers. So beds, on the other hand, are common in coarser grained rocks such as conglomerates, sandstones and limestones, and they will typically form in environments that give you a slightly higher rate of deposition. Higher rates of deposition means more sediment. More sediment means thicker layers. So the surface that separates one bed from another bed, or one lamination from another lamination, is typically referred to as a bedding plane. So above and below, the rocks will differ in composition, texture and colour. So if I have a layer of rock and I can see there's a layer of rock below it and a layer of rock above it, well, the reason that I can tell that the layer of rock above and below it are different is because there will be some difference in composition. They'll have different clasts in it, for instance, different fossils. There'll be some difference in texture. Maybe, one layer will have ripple marks, one layer will have crossbeds, and one layer will have mud cracks. And there'll be differences in colour. Once again, differences in colour make it quite easy to distinguish between the beds. So here we go. So here's an example of some laminations. So this, just to give you an example, this is a 50p piece. It's slightly larger than a quarter. And you can see, quite clearly, these layers are on the whole very, very thin. Now, compare that to this sequence of beds here. So you can see these layers, on the other hand, are much, much thicker. So they're going to be classified as beds rather than laminations. But we can also see that this is a sequence of different rocks. We can see, especially here, for instance, we have this layer of sandstone here, which grades into this layer here. This layer here actually has this very distinctive orange streak in it, which grades into another sandstone here, another layer of something there, another sandstone here, another layer of something here. So between each of these layers, there are differences, and we can see the differences, can't we? And that's what allows us to actually distinguish between this layer and this layer. It tells us that we're moving from one layer to another. And these differences are essentially seen in changes in composition. So in this case, we go from sand size class here to silt and clay size class here. Then we'll have changes in texture. Well, there might be textures in this, in this sandstone here, for instance, like ripple marks, that would tell us maybe it formed on a beach. In contrast, these muds here might have textures that tell us that it formed slightly further out to sea. And then we'll have, obviously, colour. And colour is obviously a reflection of the minerals that make up a rock. So, this rock here, because it's made up of different minerals, is going to have a different colour to this layer of rock here. And these laminations, and these sandstones, these textures are not only present on Earth, they're also present on other planets. So this is a sandstone on Mars, and you can quite clearly see we have lots and lots of layers. They're approximately a centimetre thick. So what we have is lots and lots of centimetre thick size beds of sandstone. And so, we can see this stuff not only happening on Earth, but on, other planets in our solar system. So the next thing we have to think about is grading. So grading refers to a steady change in class sizes in a layer. So most of the time, if you think of a layer of sandstone, the class are going to be the same size from the bottom of the layer of sandstone to the top of the layer of sandstone. There's going to be no change. However, some layers of sedimentary rock will have a change in class sizes as you go from top to bottom or bottom to top. So typically, the class size will decrease up through a layer. So that's called normal graded bedding. So once again, in the case of normal graded bedding, what you're going to have is you're going to have a layer, and you're going to have the largest class at the bottom of that layer, and you're going to have the smallest class at the top of the layer, and you're going to have a gradual transition in class sizes going from the bottom of the layer to the top of the layer. So that's normal graded bedding, and that's by far and away the most common type of graded bedding. On the other hand, if the class increase in size as you go up through the layer, that's called inverse graded bedding. So we'll have the small class, the silts and the clays, for instance, at the bottom of the layer, and then as you go up through the layer, you might have the medium sands, and then the very coarse sands at the top of the layer. Now, inverse graded bedding is a lot rarer than normal graded bedding, but it does still occur. And once again, graded bedding is reflective of the type of environment in which the sediment was deposited. So most graded bedding is deposited by short-lived energetic flows like turbidity current. So a turbidity current is a landslide underwater in the oceans. And these flows of sediment will roll down hills, roll down slopes underwater. And obviously, just like a landslide on land, as they flow down the hill, they pick up speed, and then obviously once they stop moving down the gradient, they lose velocity quickly, and they'll deposit the sediment. So typically, we can say that in most cases, these energetic flows have to be relatively high energy because you require a high-ish energy to move a range of class sizes. Okay, so typically if you have a very limited energy, you can only move relatively small class sizes. So you're not going to really end up with any kind of grading because the sediment you produce will have a very limited range of class sizes. So typically, when you have one of these energetic flows, so let's think of one. Let's imagine one of these landslides underwater, these turbidity currents. So as the sediment falls down the slope underwater, obviously it will start picking up velocity. It's going faster and faster and faster because it's accelerating under gravity. And then all of a sudden it stops going down, so the slope disappears and it moves onto a flat, relatively horizontal surface. Well, as soon as it does that, the flow is going to stop losing velocity. It's going to start losing velocity. As it starts losing velocity, it starts losing energy. As it starts losing energy, it loses its capacity to carry certain class sizes. So as it loses energy, it will have to start depositing the largest class sizes first because they weigh the most. So as it loses energy, it has to, let's say, dump the coarse sands. So it gets rid of them first. So they're at the bottom of the layer. Then as the flow continues to lose energy, it then has to dump the medium sands, then the fine sands, and then eventually it starts depositing the silts, and then finally the clays. So essentially what you're seeing there is these normal and inverse graded beddings are caused by a flow, relatively short-lived typically, and that flow will slowly lose energy, and that will cause the sediments to be deposited in a set order. So a turbidity current, one of these underwater landslides, is denser than the surrounding seawater, so it sticks to the seafloor. So it will stop once it starts to flow over a relatively flat surface like a lake floor or the abyssal plain in the deep ocean. As it slows, as I was just saying, it therefore decreases in energy and the largest particles fall out first, followed by progressively smaller ones. Some debris flows, on the other hand, like pyroclastic flows that come down the sides of volcanoes, or very, very large landslides, will transport larger class on a layer of finer material. So just think of Christmas. There's the possibility that at Christmas you might have gone to Costco and you could have ended up with one of those huge containers of nuts. It contains cashew nuts and Brazil nuts and and all the rest. And if you've looked at that, obviously you have a range of class sizes. You have the smaller ones like your pistachios and your peanuts, all the way up to your larger ones like your Brazil nuts. Now, if you take that very, very large container of nuts and you shake it, what you'll notice is that as you shake it, the big nuts start to move to the top and the small nuts fall down to the bottom. And that's simply because the small nuts fall down in between the gaps between the larger nuts. And so, if you do that to this tin of nuts, you'll end up with all the, the really big nuts, like the pecans and the Brazil nuts on the top, and you'll end up with the small nuts like the pistachios and the peanuts at the bottom. And the same thing happens when you have things like pyroclastic flows coming down the side of volcanoes or very, very large landslides. So in that case, the layer comes down the side, down the hill under gravity. The shaking as the layer moves down the hill causes all the fine material, the clays, the silts, the sands, to fall down in between the bigger blocks, your gravels, your cobbles, and your boulders. And so that means you end up with a layer that's moving down the side of the hill that has all the fine material at the bottom of the layer and the coarser material at the top of the layer. So when that layer of material eventually comes to a stop, well, obviously it's going to deposit the stuff at the bottom first and then the stuff at the top last. So you end up with this inversely graded layer. So these diagrams here just give you an idea. So here's normal grading, larger class at the bottom, smaller class at the top, younging upwards obviously. And here's inverse bedding, smallest class at the bottom, largest class at the top, once again younging upwards. And this gives you some idea about a turbidite sequence. This is in the textbook, and you can see quite clearly, this is where the turbidite sequence comes from. So the sediments come up here off the continental shelf, they fall over the shelf break, and they come hurtling down the continental slope. And as they come across the continental rise, they move into the abyssal plain environment, the deep ocean, where as you can see, the gradient slowly shallowing out. As the gradient shallows out, the flow begins to lose velocity, and as it loses velocity, it will deposit the largest class sizes first, and then progressively smaller ones after that. And so you end up with this layer of sediment that's coarsest at the bottom and finest at the top. And so that's, your sequence of sediments deposited by a turbidite. So you can see it here. So here are two examples. On this side, we have normal grading, and on this side, we have inverse grading. And so what can we see? So here we can see, here are several, these are actually turbidite sequences. And you can see at the bottom of each turbidite sequence, you have this darker layer of coarser sized sandy material. And as you go up through the layer, the layer steadily becomes thinner and thinner and thinner. Well, not thinner. The clast sizes get smaller and smaller and smaller until you reach this point. That's where the clays are going to be. And then you have the next turbidite flow coming over the top. So then you have another layer of sand, and that layer, the clast sizes steadily get smaller and smaller and smaller as you go up. So that's normal graded bedding. So the clast size is increasing as you go down through the layer. Largest class at the bottom, smallest class at the top. Here we have inverse graded bedding. So this is from a debris flow, a landslide. And so what can we see? Well, here's the bottom of our layer, there, and here's the top of our layer, here. And what you'll notice is now the layer itself does look very powdery, but you'll notice that the smaller material is at the bottom of the layer, and you can see the larger material here is at the top of the layer. And so in this case, we have the clast sizes increasing as we go up. So that's inverse graded bedding. And normal graded bedding and inverse graded bedding will only form in very limited environments. And so once again, that gives us some idea about the type of depositional environment into which the sediment was deposited. Okay, so actually, do you know what? We've been going for over 40 minutes. There's another time for a break. So once again, pause the presentation, get up, have a walk around, get a glass of water, and please come back in a couple of minutes. Okay, so we're actually going to talk about turbidite sequences a little bit more. So turbidite sequences not only show us normal grading when it comes to the rocks that we see, they also produce a very, very distinctive type of rock, which we refer to as a boomer sequence. So a boomer sequence is a sequence of 5 different layers of rock that occur in a set order, and they are the way of identifying a turbidite sediment. They only occur with turbidites. This is one of these situations where geologists have been out, we've looked at modern environments, and we've seen that same 5 layers of rock that occur one after another, and they each have distinct textures in them, and so we know that those 5 layers of rock are related to a single turbidite flow. And then we can apply that to when we see that these 5 same layers of rock in rock sequences now. Okay, so how does a turbidite sequence work? Well, once again, the sediment itself comes off the continental shelf here, so shallow water, comes over the edge of the shelf break, and it comes flying down the continental slope, and then the flow settles out and stops on the abyssal plain down here. And you'll notice we can see the continental slope is full of these valleys. And these valleys essentially are the locations where turbidites will be focused. And so these turbidite flows will become focused down these valleys, and so you'll tend to get one turbidite flow on top of another on top of another. So this is a boomer sequence here, and it consists of 5 layers, and they're called layer A, B, C, D, and E. So as you can see, as we go up through the layer, the size of the sediment is getting smaller. So coarsest material at the bottom, finest material at the top. So we have normal grading as we go up through these 5 layers. So each layer has its own distinctive appearance. So at the bottom, typically the bottom of a turbidite is marked out by what we refer to as scouring. So if we just go back for a couple of slides, here we go. We can see that if we look at the top of this turbidite sequence here, the bottom of this layer here, we can see it's very, very uneven, highly irregular. And that's because as this turbidite sequence came through, it ripped up the top of the previous turbidite flow. And so that means that the bottom of a turbidite flow is typically going to be rather chaotic. Anyway, so above this chaotic base, you have a massive layer of sands. That's a layer of sand-sized particles that have no structure to them. It's just a hot, massive sand. So above that layer of sand, this massive sand, we have layer B. And that's a layer of sand that shows parallel lamination. So in this layer of sand, we get lots and lots of fine, sub 1 centimeter size layers. So then as we go above layer B, we go into layer C, still a sand. And in this sand, we start to see ripple marks. So we start seeing the bedding starts to look very, very uneven. It looks what we refer to as hummocky. And so what's going on here is we're seeing the system slowly waning in energy. The massive beds are deposited when the system is at its highest energy. So it's such high energy that no textures can form. Okay, no sedimentary structures can form because there's so much energy. As the energy begins to drop, we get the simplest structures forming. So that's laminations. And as this energy continues to drop further, we get a more chaotic flow, and that begins to produce, ripples. And so on there, by the time we're at layer C, we have sands being deposited that have ripples in them. Now, as we continue from C to D, the class size gets smaller, and we go from sands to silts, and these silts will show laminations once again, very, very fine layering. And then above the silts, we'll have a layer of clay, which will just be massive. And so down here in the right, we can actually see a modern example, well, not a modern example, but an example of it actually in a rock face. So here we go. So here are our sequences A, B, C, and D. Now in this case, we are missing E. Okay, it's either covered over by these rocks up here, or it's just been completely lost. Anyway, so at the bottom here, we can see we have this coarse sand down here, and you can quite clearly see that, well, you can see it's coarse, you can see the individual grains, but once again, you can see there's zero structure. So that's our massive sand at the bottom of our boomer sequence. Above it, we have layer B. We can see these nice, fine, horizontal laminations in the sandstones. That's layer B. By the time we're up into layer C, which starts about here and goes to about here, we can see we have these highly irregular layers. They kind of go up and down. Now that's going to be our ripple marks. That's layer C. Then as we move into layer D, we can see we have this slightly darker coloured layer, and you can just about make out the layers within it, so that's going to be layer D. Now below layer A here, right down here, you can see there's this kind of featureless dark grey layer. That's going to be the E layer from a previous turbidite flow. Okay, so this is a boomer sequence, and boomer sequences only form in turbidite flows. So once again, it's a situation where sedimentary geologists have been out, they've gathered evidence from modern turbidite flows, and that evidence has been applied to ancient rocks, and so that allows us to see turbidites that have happened in the past. And so once again, the second we see this boomer sequence, we know that we are underwater, and we know we're essentially at the position where the continental slope ends and the abyssal plain begins. So next we have crossbedding. So I'm sure you remember crossbedding from physical geology, but we're going to go over it again anyway. So crossbedding is produced by the migration of sediment upper dunes windward face, which is called the stoss, and its deposition on the downwind side, which is called the lee. So when sediment is blown by the wind or moved by water, okay, so we can get dunes in both desert environments, and we can get dunes forming in very, very large rivers like the Amazon or the Mississippi, for instance. And so what's happening in a dune is sediment is moved up the stoss side of the dune, and then it gets deposited down the lee side. So sediment goes up the stoss and down the lee. Now, essentially, a dune actually moves by cannibalizing itself. So what a dune does is it takes sediment from its back, transports it up, and deposits it at its front. So it's constantly essentially eating its tail to essentially feed itself at the front. So that's how a dune moves. Now, as the sediment goes up and is dropped down, the layers of sediment that are deposited down the lee essentially form these layers. You can see them here, these angled layers. And these are referred to as crossbeds. So crossbeds are quite useful because, number one, once again, they give us some kind of idea about the environment, but they also tell us about the direction in which the transporting medium was moving. So as you can see, sediment goes up the stoss and down the lee. So in this case, the lee slope, so in this case, the slope goes from essentially the top left up here, and it drops down towards the bottom right down here. So we have this slope here. Well, that tells us that this dune is moving towards the right-hand side of the image. If the slope was going in the opposite direction, so from top right up here to bottom left down here, well, that would tell us the dune was moving in the opposite direction towards the left-hand side of the image. So they're very, very important in that respect, but they're also helpful because each one of these crossbeds will typically be narrower at the bottom and wider at the top. And this means we can use them as what we refer to as way up indicators. They can tell us which way is up, which might sound, quite obvious, but to a geologist is very, very important. So, you need to know which way is up in a layer of rocks. So because these crossbeds are narrow at the bottom and broader at the top, when we see a crossbed in a layer of sedimentary rocks, well, we know the narrow end has to be the bottom, and we know the wide end has to be the top. So we know essentially that way must be up. So you can see it a bit more clearly in this diagram here. So in this diagram here, we can see, so here are our crossbeds, and you can see they are narrowing towards the bottom, and they are broadening towards the top. So we know this has to be the bottom of the layer, and this has to be the top of the layer, therefore that is up. And we can also see, as I discussed, that the angle of the crossbeds tells us the direction of travel. And so we can see here, so these crossbeds are going from bottom right, top right up here, sorry, to bottom left over here, so we know that the sediment is being transported off to the left. In this case here, the sediments are going from top right up here to, sorry, let me try that again, to top left up here to bottom right down here, so we know the sediments are being transported to the right. Now you'll notice that in this sequence here, we have lots and lots of crossbeds one on top of another. And that's because dunes essentially will grow over the top of each other. And you can see it happening here. So here we have a dune, and it's migrating along, and this dune then starts following it over the top of the earlier dune. And we can see that as this dune is moving along, it's actually planing off the top of the material here. Okay, so every dune will kind of plane off a flat surface across the crossbeds from the previous dune. All right, and then this dune will grow over the top of this dune here, then another dune will come over the top of this dune here, and you'll end up with a sequence of crossbeds stacked one on top of another. And so we can see that here. So here are our sequence of crossbeds, and we can see it. Now, of course, it would have helped if I put some lines in, but nonetheless, so you can see the crossbeds here. So you can see them in this case, they're starting over here, and they're dipping off towards the left. You can see them here as well, starting here, dipping off towards the left, down here, starting here, dipping off towards the left. So they're going from the up portion here, dipping off in this direction. So this tells us this sediment was being transported this way, off towards the left. So this layer is being transported to the left, this layer is being transported to the left, this layer is being transported to the left. Now, look at this layer here, on the other hand. We can see the layering goes from up here, and it dips off towards the bottom right. So that tells us that this layer here was being transported towards the right-hand side of the image. So that's the interesting thing about deserts. The wind doesn't always blow in one direction. Sometimes it will change. And so that means crossbeds will end up going in multiple different directions. But nevertheless, on the whole, we can see that the normal direction of transport in this area, based on this image, was towards the left, because this layer is going to the left, this layer is going to the left, and this layer is going to the left. So that tells us the prevailing wind was going from right to left. And in this case, this layer here has clearly been formed by a reversal in the wind direction. And we can even see crossbeds in these river sediments. So here we go once again. Now these are on a much smaller scale. Nevertheless, you can see there's a quarter there for scale. But you can see them. There we go. You can see you have crossbeds starting up here and dipping off down here. We can see them here as well. We can see them here. And once again, that's going to give us some idea about the direction of transport. We can see that based on this crossbed, starts up here, comes down over here. So we know the sediment has to be transported towards the right-hand side of the image to form those crossbeds. So they're very, very good indicators of the direction of flow, and in the case of large crossbeds like in dunes, they also give us a way up indicator. So next we have ripple marks. So if you've ever been to a beach, you probably have seen ripple marks. In fact, you've probably walked over ripples. So ripples consist of alternating ridges, which are the high points, and troughs, which are the low points. And ripples are caused by a current, so that's wind or water, where there's only one direction of flow, so that's called unidirectional flow, produce a distinctive type of ripple, which is called a current ripple. And these current ripples are asymmetrical when we look at them, and you'll see that in greater detail in a couple of slides' time. So, as with dunes and sediments, the same thing goes for ripples. So sediment will move up the stoss side of a ripple and be deposited on the lee side of a ripple. Now, to be clear, in the case of most ripples, you won't get little crossbeds forming. You'll just see the ripples themselves. So these asymmetrical ripples, these current ripples, are excellent indicators of ancient current directions. They tell you which way the water or the wind was blowing or moving. On the other hand, we have a different class of ripples, which are called the wave-formed ripples, and they're produced by the to and fro movement of waves as they hit the beach. And these will produce ripples that are symmetrical in profile. So essentially the ripple will have limbs which are the same length, and they are at the same angle. And that's produced by bidirectional flow. So the easiest way to think of bidirectional flow is think of a ripple hitting think of a wave hitting a beach. Well, as the wave hits the beach, the water from the wave goes up the beach, doesn't it? So it's transporting the sediment up the beach. However, obviously that water is going to eventually come to a stop, and then gravity is going to kick in, and it's going to be pulled back out towards the sea. Well, as it gets pulled back out towards the sea, obviously the water is going to pull the sediment back down the beach. So as the wave moves up the beach, it pushes sediment up, and as the wave comes back down the beach, it pulls the sediment back down. And so we have a bidirectional flow, one way up the beach, one way down the beach. And so that means the ripples we form are symmetrical. And so this diagram here kind of gives you some idea. So here we go. So here are asymmetrical ripples. These are the current ripples. They have a stoss side, a long side here, and they have a lee side, a short side here. So sediment comes along the stoss and gets deposited down the lee. Okay, and just like a dune, the angle of the shape of the asymmetrical ripple tells us which way the water was moving. So here's a picture here. We can see we have the long sides here. So that's the stoss side, and here we have this much smaller lee side. So stoss, lee, stoss, lee. And so that tells us the water must have been moving towards the bottom left of the image. Now, then we have waveformed ripples, or symmetrical ripples, as they're also called. And you can see in the case of symmetrical ripples, both limbs are the same length, and they have the same angle. And that's caused by bidirectional flow. The flow goes one way, and the flow goes another way. And the most common way of doing that is with waves hitting a beach. And so as we can see, this is a modern example here, and you can see, so here are ripples. This limb here and this limb here are the same length, and they're at the same angle. So we would classify this as a symmetrical ripple. And then straight away, as soon as we know that, as soon as we see symmetrical ripples, you instantly think to yourself, right, this sediment was probably deposited in some kind of beach environment. And so, once again, it's an example of sedimentary geologists going out to modern environments, finding these structures and, working out, where they form and how they form. And so when we see them in the rocks, we can then apply that to the rocks, and we can work out where the sediments that form those rocks were deposited. The next thing to look at is mud cracks. So mud cracks are something we're probably intimately familiar with, especially if you lived in an area that was flooded during Hurricane Harvey. So mud cracks form when we have a moist, clay-rich sediment that dries out. So as this very wet, muddy sediment dries out, it will begin to essentially contract. And as it contracts, the layer itself will crack, especially the top of that layer. And it will form a set of distinct polygonal shapes. So you get lots of pentagons and lots of hexagon-like shapes forming. And these are called mud cracks. And so the presence of mud cracks in rocks means that the ancient sediment was deposited in an environment where we have alternate wetting and drying portions. So such environments would include environments like lake margins, maybe river banks, floodplains around rivers, or along the seashore, especially deltas. So, in all these environments, you'll have the deposition of, a very wet, moist, muddy sediment, and then that will be exposed for a period of time. That will dry out, it will crack, and then a new layer of sediment will get deposited over the top, and those cracks get filled in. When the cracks get filled in, they will be preserved in the sediment, and maybe could be preserved when the rock gets lithified. So here we go. So here we have some modern examples of mud cracks. So you can see one here and here. Okay, so you can see, so this is a case of a very muddy sediment. You can see it's dried out, and you can see all these cracks. We have lots of, pentagonal and hexagonal shapes, also quite a few square shapes as well. We can see this here. So this is a modern river environment, and we can see the river level for this river clearly changes. Sometimes the river level is higher and this sediment here is wet, and then the water level drops, and so this sediment gets exposed and it begins to dry out and crack. And so once again, these are mud cracks. Now, when the next layer of sediment is deposited over the top, if it gets deposited fast enough, it will fill in the mud cracks and they'll be preserved. And so we can see that here. Here are some ancient mud cracks, and we can see, so these are the shapes themselves. That's this area's here, and these slightly darker lines here represent the cracks in between these pieces. And so this tells us this sediment was deposited in an environment where the wet sediment was deposited, it dried out, and then the cracks were then filled in very quickly by a layer of sediment later. Now in this case, this is actually an impression. So this is actually the layer of sediment that fills in the mud cracks. So the mud cracks themselves have been lost, but the sediment that filled in the cracks in between these pieces here actually persists. And so in this case, we have essentially the imprint of the mud cracks. But in both cases, this gives us very strong indications about the likely environments in which the sediment was deposited just by looking at these textures. Okay, so we've been going for over an hour, so take a minute, pause the presentation, get up, have a walk around, get in a glass of water, and come back in a couple of minutes, please. Okay, everyone, not too much longer to go, so let's get through these last few slides. All right, so those were physical structures produced by the movement of the sediment. The other types of structures that we can get in sedimentary rocks are biogenic structures. So those are structures that are left by essentially that are caused by organisms. A classic example would be burrows, and you can see them here. So here's an example of a nice burrow. You can see it coming up there. There's another burrow coming up here, another burrow. Burrows all over the place. Now these kind of structures are important. If we know what organism formed those burrows, for instance, and we know the environment in which it liked to live, that will give us some idea of what type of environment the sediment was deposited in. So, also very, very helpful. Okay, so biogenic structures, they're essentially the deformation left by the actions of organisms on sediments, and they produce these biogenic sedimentary structures. And such structures include tracks, trails, and burrows. And such features are also called trace fossils, and in some cases they can make very good way up indicators. Once again, they tell you in a layer of rock which way is up, which way is the surface of the earth. And extensive burrowing, on the other hand, can actually be quite bad. So if we have a nice sedimentary layer with wonderful structures in it, if you have lots and lots of worms burrowing through it, well, unfortunately, it can destroy those physical sedimentary structures. When that happens, that's called bioturbation. So bioturbation is often quite annoying because it means you lose information. So here we go. So here's a nice example. So we can see here we have the tracks of a horseshoe crab, and there's actually the horseshoe crab itself fossilized there. And so once again, we can see these tracks. Now horseshoe crabs leave a very distinctive set of tracks. And so that tells us something about the likely environment. So, well, we know from modern horseshoe crabs, they tend to like to live in relatively shallow, warm water. So even if we found this rock like this and we didn't have the horseshoe crab fossil, we could look at the tracks and say, right, those were left by a horseshoe crab. And so instantly we know that that sediment was in all likelihood deposited in warm, shallow water. Obviously down here we have a human footprint. Okay, this is from the Pleistocene period, so essentially, that's over 200,000 years old. So this is essentially probably not a Homo sapien, it's probably one of the earlier members of the genus Homo. And so we can quite clearly see, though, this footprint has been left in this muddy, cracked sediment. So once again, this is clearly a sediment. It was in some kind of, wet-dry cycle, like along maybe the edge of a river. But once again, we have a footprint here. Well, we can say with relative certainty, then, this sediment was definitely not deposited in the marine environment. We can say instantly that this sediment was definitely deposited on a continental environment. So just by looking at this one track, we instantly have some idea about where the sediment would have been deposited. So then we have things like burrows. And burrows are extremely useful. Number one, they can tell us which way is up. And number two, they can tell us what kind of species formed them. And so each type of burrowing organism, in some cases, they'll form very, very distinctive burrow shapes. And so even if we don't have the organism itself, if the burrow is preserved, we can work out what organism formed it, and therefore what type of environmental conditions the sediment was deposited in. Now, on the other hand, here we have bioturbation. So here we have some ripple marks. You can see they're running approximately top to bottom. And you can see cutting through it, we have all of these channels. Okay, now these are essentially burrows made by worms burrowing through what looks like quite a muddy, sandy sediment. Now, in this case, they're not too bad because you can see the original physical structures underneath. However, imagine if you had a lot more of these worm burrows. Well, obviously these original ripple marks would be destroyed and we would lose that information. So bioturbation can be, not a bad thing, and in some cases it can be a very bad thing. So here's a summary of sedimentary structures. So first of all, we have the physical ones, so laminations, beds, graded bedding, cross-bedding, ripple marks. Ripple marks are split into current ripples and waveform ripples, and then we have mud cracks. And then we have biogenic structures, things like trace fossils. So these are all the types of sedimentary structures that geologists will use to try and get some kind of idea as to which environment a sediment was deposited in. So obviously once we have this information, we have to interpret it. Now we need to remember that no sedimentary structure is exclusive to one regime. Most sedimentary structures will occur in one or more type of depositional environment. So for instance, we can get ripples in deserts, we can get ripples forming on beach sediments, we can get ripples forming in rivers, we can get ripples forming in tidal channels on deltas, to name but a few examples. So ripples can form in a whole range of different environments. However, it is the associated sedimentary structures, along with other sedimentary rock properties, that actually allows geologists to make environmental interpretations with a high degree of confidence. So, for instance, we will also look at the geometry of the sedimentary rock. So that's when we think about the three-dimensional shape of a layer. Now, in most cases, a layer of sedimentary rock will often just be flat and lateral, and we refer to that as essentially a sheet. Okay. Now we need to bear in mind, as I'm saying here, that caution must be used, as the same geometry can be found in more than one environment. So sheet geometries, where we have these, relatively flat, laterally extensive layers, they occur in lots of environments. So that kind of geometry isn't particularly helpful to us. But sometimes geometries can be quite helpful if you use them in a conservative and careful manner. So as I was saying, when you have one of these layers of sediment that's relatively thin but spreads out over a very large area, that's referred to as a blanket or sheet geometry. Now that's relatively common, so that doesn't tell us too much. However, sometimes the geometries can be more helpful. So for instance, if we have a sand deposit that occurs at a very long, narrow layer in 3 dimensions, well, that gives us some possible idea. Now these long, narrow layers look a bit like a shoestring. And so they're referred to as either a shoestring geometry, or they're also referred to as an elongate geometry. Now that kind of geometry forms when you have either rivers. Obviously think of the Mississippi winding its way across the landscape. It forms it would form a 3-dimensional shape a little bit like a shoelace, wouldn't it? The other way we can form that kind of geometry is if we have a barrier island. So a barrier island is an island that sits just off the coast, and it has a lagoon behind it, and the barrier island essentially is like a linear island that runs parallel to the coastline. And so once again, that would give you a linear elongate line of sand that would give you a very shoestring-like geometry. Now, obviously, in both of those cases, a river and a barrier island, just it's on the coastline, there would be other structures in there that would allow you to work out, what environment I was in, and then there will obviously be other fossils as well. In a river environment, you would have freshwater fossils. In a barrier island environment, you would obviously have marine, so saltwater fossils. So, once again, you combine lots of pieces of evidence together to produce a geologic interpretation. So we have a few other geometries. We have deltas. Now in the case of deltas aren't actually that helpful. When you look at a layer of rock in a delta, you think to yourself, well, that could have formed in any way. In the case of deltas, it's all about the shape that those layers make in 3 dimensions. And when you look at them in 3 dimensions, you'll actually see that deltas make a very, very distinctive type of shape that when you look at it in cross-section, it produces a lens-like shape. It has a lenticular form, so it kind of starts off narrow at one end, gets wide in the middle, and then gets narrower at the other end of the sequence. And so that's very, very distinctive if you take a cross-section through the delta. If you look at the delta from the top down, typically it will give you a lobate morphology, so it will look like a fan. And so once again, depending on how you look at the sequences of rocks deposited by the delta, if you look at them in section, so from the side on, you'll see this lens shape. If you look at them from the top down, you'll see this lobate or fan-like shape. So once again, that tells you the type of environment in which the sediment may have been deposited. And then of course we have coral reefs. Coral reefs will obviously give rise to limestones. So buried coral reefs will present a very long, irregular, narrow band of coral-derived carbonates. So what you'll see is you'll see a limestone that's made up of lots of bits of broken up coral. And then when you track that layer of limestone, you'll see it forms this very long, narrow, irregular band. And so that's going to tell you that you're going to instantly know that this limestone was deposited by a coral reef or formed in a coral reef environment. So when we think about the fossils, they're also going to give us more information. So of course the fossils represent the remains or traces of prehistoric organisms that have been preserved in the rock. And they can be used to stratigraphically, they can be used in stratigraphy to relatively date and correlate layers of rock. They are also important constituents of some rocks, particularly limestones. We need the shells to actually make the limestone. So when present, they are useful for determining the deposition environment in some cases. There are some organisms that only like to live in a very limited range of environments. So two factors need to be considered when we use fossils for environmental analysis. The first one is, did the organism in question live where it was buried, or were the remains transported there? So a good example is this. If you find dinosaur bones, it's pretty safe to assume that the sediment that contains those dinosaur bones was deposited on land. So you can say maybe something like a river floodplain. It makes sense, doesn't it? We know there's no such thing as a marine or flying dinosaur, so therefore if you find dinosaur fossils, that dinosaur has to have been living on the land. However, if we find dinosaur bones that occur in a layer of rock, a bed of rock, along with coral fossils and shelly organisms, we must assume that either the carcass was washed out to sea, or the coral or shells were washed onto land. So if the dinosaur body fell into a river and was transported out by that river and the body was deposited in the ocean, or on the other hand, maybe there was a tsunami, and that tsunami pulled up loads of pieces of coral and shell as it was heading inland, and it deposited those pieces of coral and shell onto the floodplain, and at the same time maybe killed the dinosaur. So the other thing we need to think about is, what kind of habitat did the organisms originally occupy? So that's also going to be quite helpful. So we must study the fossil structure. So for instance, did the fossil have a thick shell or a thin shell? Was it elongate or equant? Did it have spines? And from there we can start to draw conclusions. So a classic example is this. So a lot of organisms that live in sediment, so when organisms that bury themselves, don't have spines. They have very smooth shells. That makes it obviously easier for them to move in and out of the sediment. On the other hand, if you have an organism that likes to live on the seafloor, think a sea urchin, well, lots of sea urchins have very long, very scary spines on their back. Obviously, because they're on the seafloor, they're exposed. If you're exposed, if you want to try and survive, you need to have a defense. In that case, a good defense is covering yourself in big, scary spikes. And so, that's one way they protect themselves. Now, the second we see spines, we think, right, this animal was clearly living in some type of environment where it was exposed. And then we have to think about things like shell thickness. So let's look at the two examples at the bottom. So clams have thick shells. Now they typically live in shallow marine environments. So where you have a clam with a thick shell, that typically means they live in these shallow, warm marine environments where there's lots and lots of predation. Okay? So that means there's lots of stuff around that will try to eat the clams. And so the clams have to develop thick shells to protect themselves. However, if you find a clam that has a relatively thin shell, well, those types of clams typically live in relatively low energy environments where there's a much, much lower rate of predation. So that typically means they don't have to expend so much energy on defenses because, the chances of them being eaten by something are lower. And also, they don't have as much energy to expend on building a thick shell in the first place. So the shell they get the shell they form for themselves is relatively thin. Another good example are corals. So corals like to live in warm, clear, shallow marine environments, where the symbiotic bacteria and other organisms that live in the corals can carry out photosynthesis, and where there are plenty of microorganisms to filter from the water. So once again, the environment in which we find corals allows us to instantly work out what type of environment the sediment would have been deposited in. So the second we see a limestone that contains coral fossils, we instantly know that limestone was deposited in a warm, shallow marine sea with relatively nice clear water. So we also have these microfossils. We've already touched on them in the past. These are the fossils that we can't see when we look at the rock in our hands. We have to use a microscope to see them. And once again, they're extremely useful because certain fossils will only occur in certain water temperatures, or water that has certain salinities, or water that has a certain oxygen content. So when we drill for oil, we'll typically produce things called rock chips. So as the drill rig drills down through the layers of rock, it will be punching its way through the layers of rock, and it will produce lots and lots of small chips of rock as it does it. And these chips of rock get pushed towards the surface, either by typically using pressurized water. It pushes them out of the borehole, and they'll be collected by a geologist, who's referred to as a mud logger. And that geologist will collect these chips, and in the chips there will be lots and lots of microfossils. And the microfossils can be analysed later on, and they can allow us to do things like they can allow us to date the layer, and they can allow us to do an environmental analysis. Okay, and that will allow us to work out things like, what was the water depth, what was the water temperature, how much light was there, were there lots of nutrients around, and so on and so on and so on. And that will excuse me. And that will allow us to work out whether the layer of rock we're looking at would have been a good or a bad candidate to make oil. And so, if it's a good candidate to make oil, we can say, right, if this layer reached the right temperatures and pressures, it would have started making, oil and gas. And then we think to ourselves, right, where would that oil of gas have gone once it was formed? And then that's the next part of the hunt. So microfossils are also useful as it helps geologists to distinguish beds that can and can't produce oil, as I just said. So in some cases we've already touched on, fossils may not be present, however we may have the trace fossils, and they can be indicative of certain environments. So as we were saying, horseshoe crab tracks means that essentially the sediment was probably deposited in the environment where modern horseshoe crabs live, and modern horseshoe crabs tend to live in relatively warm, shallow seas. And you can see in this diagram here, this is a diagram that shows what we refer to as ichnofacies. And that's the use of different burrows to identify where you are. And as you can see, so as you go from the coastline over here down into much deeper water, very deep water, like the very deep ocean over here, the abyssal plain, you can see you get distinct changes in the organisms that live in these areas, and therefore you get distinct changes in the burrows that you see. And so, this means essentially we have a tool that allows us to work out, number one, what environments, what organisms were there, because each of these burrow shapes is related to a single type of organism. And then from there we can work out how deep was the water. Shallow over here, very deep over here. And so burrows are extremely useful to us. And to finish off, here's quite a nice example. So this is an example of Miocene beaver burrows. So during the Miocene you had large areas in North America that were once covered by forest. That forest began to die away. And so the beavers that were living in those environments, well, they had to make a choice. Did they try and find new forest, or did they try and live in the now deforested environment that they were in? And some burrows decided to live in this deforested environment, and they decided the best way to protect themselves was to burrow underground. And so they did. They produced these extremely interesting spiral burrows to get down. Then they had these horizontal burrows under here that would lead to their living chambers. And so, and so that's, once again, another very interesting way to, number one, it tells you about the environment, tells you it would have been dry and relatively sparsely forested. Okay, tells you about the organism, and it also gives you some idea about the environmental history as well. It shows you that, well, as we know, beavers like to live in forested environments. Well, when a beaver decides to start burrowing underground, clearly the forest they like to live in has been lost and it's been replaced by some environment which has forced them to move underground for protection. Okay, so that's the end of the presentation. So once again, please don't forget to make a note of the code word. Remember, you're going to need it for the quizzes. And that's all. I will see you in the lab class.